Before diving right into looking at some nonlinear systems, I want to give a little bit of a primer on some of the visualization and analysis methods we're going to be using when we're looking at a nonlinear system. But first I want to apply them to a linear system like those that we are familiar with. So we already know how these systems are going to behave, so we're going to see kind of looking at them through a little bit different lens. So the first tool we're going to look at is the use of the phase plane, which is going to happen when we have 2 state variables, or phase space when we bump it up to 3 variables. And this would also work in higher dimensions as well. But what this is a visual method. We'll use it as where we can visualize the dynamics of our system in this phase plane. And really all it is we're going to be plotting our state variables against each other, and time is going to be a parameter, rather than the usual way we've been looking at the behavior of our system, where we would plot position versus time or velocity versus time. Here, we're going to plot like position versus velocity and see what the trace is in this phase plane. What this will let us do is assess the behavior near our stability or equilibrium points, and we're going to be able to see, is this going to be a stable or an unstable system near this equilibrium point? And we can see, does it asymptotically approach zero or not, if it spirals around that point or if it doesn't spiral around that point. I won't get too into this, but we'll see in our example what an underdamped system is going to look like, where it's going to approach the equilibrium point with a spiral. Now, let's apply this to a system that we're familiar with. We've seen dozens of times before, just a simple spring mass damper system. And we'll keep it unitless for now, so it's very generic. So we'll have a mass of 1 unit, a spring constant of 3 units, a damping coefficient of 1 unit. Now, a little bit different than the systems we've been looking at, we are going to look at this as an unforced system. So that f of t is 0. No external forcing is going to act on this system. It's going to be completely autonomous. So we will give it non-zero initial conditions, a position of 1 initially, and a velocity of 0. Now, we can look at these systems when they're forced, but that's going to be outside the scope of what I want to focus on in this lecture. So we're going to give it these initial conditions, let it go, and see how the dynamics progress. And we're going to be doing this in a state space format, so initial conditions are going to be easy to put into our ODE solver. That's not going to be a problem. It'll be a little bit trickier if we try to do this with transfer function, but I'm interested in looking at all of the states of this system, which we're going to see are going to be the position and the velocity of the mass, 2 states it's going to take, and I want to find the response numerically using ODE45 with our state space model. And then I'll make time trajectory plots. That's what is going to be the typical plots we've been looking at. And also I want to look at the phase space, or really it's going to be a phase plane in this case. Okay, so the first step is we want to solve this numerically. We want to see what's happening to the position and the velocity over time. So jumping into our MATLAB, I'm going to set this up for our state space model. So actually I'll start there. This is going to be the state space model we have for this system. So it is a linear system for right now, which we are familiar with. And the A matrix, if we go back to when we first learned about state spaces, we already know what format it should be in for this simple spring mass damper, 0, 1, negative k over m, negative b over m. So I set up this L10 lin function. This is actually from lecture 10. I'm just going to reuse it here. So I'm setting it up so that the inputs it takes are going to be time, the states, which I'll call x, that's going to represent the 2 states in our system. Again, state x1 is going to be our position, x2 is going to be our velocity. So x is our vector of states, and this is set up so it can take different masses, different damping coefficients, and different spring constants. So when we use this state space model to feed into ODE45 or another ODE solver, remember, really its only job is to assemble this column vector of the derivatives of our states. So xd is going to be x1 dot, x2 dot as a column vector. And for linear systems, we can set it up nicely. That's just going to be a times x. When we get to our nonlinear systems, we're still going to have the same idea. xd is still, or x dot still has the same job, but we're going to have to assemble it manually. And just to point out here a little MATLAB thing, it's underlining this t and saying that I don't really need to use it, because here in this system, because there's no forcing, nothing here is purely dependent on time. So it's actually not using the t, even though I specify it up here as one of my arguments into my system. So it's saying that I could replace it with just a tilde, but I can also just leave it as t. It's not going to be a big deal for what we're doing to have this extra variable coming in. But just do note that we're going to give it a t value, but it doesn't really do anything. Okay, so this is just setting up our state space model, which is just going to return our column vector x dot, which is x1 dot, the derivative of position, and x2 dot, the derivative of velocity. So again, I did skip over the modeling steps, but we've done it many times before. We just need to get the state space model for this system. Okay, so now back to how are we going to solve our system. So here I was told that the initial conditions are going to be what drive the dynamics of the system. So the initial position I'm setting to 1 and the initial velocity to 0. And I'm going to use the parameters as specified on the slide, a spring constant of 3, mass of 1, and damping coefficient of 1 as well. So since I looked at the system prior, I know that by 12 seconds it's going to pretty much settle down. So I'm just going to simulate this for 12 seconds in increments of 1/10 of a second. So 16 is doing really the numerical solving here. I'm using ODE 4.5. Again, just as a refresher here, the way I'm going to be implementing it, I'm using this, this function handle, this at. So the way I do it is the first thing is what variable I'm calling the time. I'll call that t. And then the second variable is what I'm going to be calling the states. Here I'm calling it y. It doesn't matter that in the other M file I called it x, because this is going to know that I'm feeding y into it, and in the other function file it knows, oh, that thing is the states. So I could call it y here, or I could call it x. It really doesn't matter here. So t comma y, then the name of the function that is containing my state space model, which we just looked at. And then I have all the arguments in the same order, so notice they have to be in the same order here. T, Y, M, which it's getting from above, B it gets from above, K it gets from above. So T and Y are going to be determined by ODE 4.5. That's why I have this at sign here. But M, B, and K are coming from parameters as before. All right, comma, and then the time span I wanted to analyze. So I'm specifically saying analyze this or give me back my states at these specific times from 0 to 12 in increments of 1/10 of a second. And then finally, the initial conditions. Since I have two states here, I need two values in my vector. My initial value at time equals 0 of my position, again, defined in line 7 as 1, and my initial velocity, or the second state variable, which is going to be defined above as 0. So what this is going to do is solve my system numerically at these time points with these initial conditions with this state space model, and it's going to return the timestamps, which actually we already know. T is going to be the same as Ti, and X is going to be a vector where each column of it is going to be my state variables in the same order. So just remember what this looks like. I'll run just up to this point. All right, so let's see what it spit out. So T is exactly as we defined it. Now, if I had not specified to use 0.1 as the spacing here, if I just in here said 0 to 12, or put a start point and an end point, then ODE 4.5 would decide what time step to take. And sometimes that's okay. Here I just want to specify it so that everything will have the same timestamps to it. So T and Ti are exactly the same right now. And then X, just to print it out, again is two columns. The first column is my solution to X1, which in this case we interpret as the position. And the second column is X2, the velocity. So again, the order of the columns corresponds exactly to the order of your state variables as you define them. All right, so we have a bunch of data here. Let's visualize it. I want to look at both of my states, the position and I want to look at the velocity. So I'm just going to run this section. It's going to plot them as these time traces. All right, so it's giving us this little animation here for how it is performing. So if we notice x of t starts at 1, well, better because that was our initial position. And the bottom, our velocity starts at 0. Again, better because that was our initial condition. And we see that by the time we get to the 12-second mark here, both of them look pretty flat, meaning the velocity has gone to 0 and the position has gone to its equilibrium position, which is also 0. And we see this is an underdamped system. Now again, we didn't really concentrate on these autonomous systems. We were looking at forced systems mostly in Unit 2. But the same idea is going to be true for when we give this an initial condition and then let go. Underdamped systems are going to oscillate around the equilibrium point like we see here, and overdamped systems are going to approach it asymptotically. So this indeed is an underdamped system. So these are the traces we are used to looking at, is typically just the position, but here we can also see the velocity. It does tell us a story of how this system is behaving. It starts with some non-zero initial position, and then given enough time, it's going to settle down into a final position of 0. Right? So back to its equilibrium position. And velocity, we're going to see it does start at 0, but because of that initial stretch of the spring, it's going to increase. The mass is going to travel vertically upwards by the definition of our degrees of freedom, and the velocity too is going to die out because of that damper. Eventually the system comes to rest, 0 position, 0 velocity. Now let's look at the same story, the same data, but I'm going to plot it on a phase plane. And we're going to see here that I'm going to plot my first state variable against my second state variable. So let me run this, and we can see in the phase plane the exact same system. Right, so one thing we notice is time is not an explicit parameter or variable in the system. It's implied because x, the position, is a function of time, and the velocity is a function of time. So by animating it, we are able to see time, because as time goes forward, we see the x and x dot combination at that time. So we started over here when time was 0, and this was our initial condition. X was 1, x dot was 0. As time went on, the states, the relationship between them, kept changing in time, and we see this nice spiraling pattern that, given enough time, our trajectory in the phase plane spiraled into 0, 0. And we saw it kept getting closer and closer, and then eventually it ended at least very, very close to 0, 0. Now, I only ran this for 12 seconds, so it's not going to end exactly at 0, 0, because it does keep oscillating around there, getting closer and closer and closer. But pretty much it has this, what we call a sink, into the center. So just for a comparison here, let's see side to side what these look at. Again, it's the exact same data. We are just visualizing it and plotting it in two different ways. On the left, with time as an explicit variable, and on the right, with time as a parameter in our system. But they're telling the same story, that we start out at 1, 0, or position 1, velocity 0, and then as time goes forward, the system is going to change, the state variables are going to change, but either way, it's getting kind of sucked onto this equilibrium point at the end, where the position goes to 0 and the velocity goes to 0.